Oh. Hello everyone. Let me first introduce myself. My name is Adam Vardashevich. You can just call me Adam. And I'm in the competitive programming. I am most known by the handle subscriber. You may be familiar with this. And I was competing in the programming contest for a long period of time. I was participating in the ICPC World Finals the years 2014 and 2016. So currently I'm not training that hard like those times, and now I'm working in the company since the previous year. But sometimes I do participate in the contest yet, and teach students in my own university and the students from different universities till this time. So I will spend this week with you. I hope I can share some interesting knowledge with you. And for today's topic, the topic itself might be pretty common, but I guarantee that everyone will know something new, because I picked this topic specifically because I think I can share some interesting features that are very uncommon among the participants, so I hope it will be interesting for everyone. So today's topic is queries on the trees, and as our general query, we will consider the LCA problem and a lot of different problems that are related with this one. So first, let's consider a tree. Everyone knows what a tree looks like. So this tree will be particularly a rooted tree. So for everyone vertex except the root one, we will have exactly one ancestor, or one exact ancestor or parent. And what is the LCA problem is the problem where for each query, for the pair of vertices, or this one, we have to find its lowest common ancestor. And the ancestor is basically the vertex you can reach by moving by the parent links. So if you pick these two vertices, the lowest common ancestor for this pair of vertices will be this one. And there are a lot of ways how we can actually find this common ancestor, and there are much more cases where we have to find it. For example, if we consider the problem where you have the queries for which you have to answer what is the length of the path between two vertices, you can just recalculate all the distances from the root vertex. So if the tree is unweighted here, it will be 0, 1, 1, 2, 3, 4, 4. And to know actually the distance between the pair of vertices, you would sum the distance to the root from this vertex, and subtract this path which is included twice. You actually subtract twice. So if you can find the lowest common ancestor for this vertex, you can solve, for example, the problem where you have to find the distance between the pair of vertices. So how we can find this common ancestor. For example, we can always find all the ancestors for the one vertex or the other one and merge those sets. Yes?
Could you please speak with the microphone here to your mouth so the sound is
Like this is better?
Yes.
Okay, sorry. So, how do we find the lowest common ancestor? Now, so we'll use the following trick. We will preprocess for all the vertices its depth. So for this picture, I've already done this because I consider that the depth is a distance from the root in the case our edges has equal weight. So, for example, we know for each vertex its depth, and we'll try to find the lowest common ancestor, for example, for this vertex and for this one. We know that this vertex has a larger depth, so we can know for sure that from this vertex we can go up higher. So let me consider some common case. I have a picture like this. Here's the first vertex, here's the second. So if you know, for example, that this vertex has a larger depth, we can iterate several times and move up by the parents from this vertex until they have the same depth. If this vertex has a larger depth, we know for sure we can do this. And still the lowest common ancestor will be somewhere from the up from both of these vertices. And after that, once we know that for this pair of vertices they have the equal depth, we can iterate them simultaneously. So we move up both of them until we have the case when two vertices matched to the same vertex. And that will be exactly the case when we came to the lowest common ancestor. So this solution may require some time because we will have the number of iterations equal to the distance by the edges between two vertices, which might be a pretty large linear number relatively to the size of our tree. So, to improve this idea, we will use a trick that is called, you can call it binary steps or binary upwards. So the idea is very similar to binary search, and provide this for the tree we will have to do additional preprocessing. So consider for each vertex I, we know its parent. Behind that, let's calculate its parent. Let's call it a parent. Let's call it something related to dynamic programming. DI, which means that the vertex, if you go from vertex E up for the 2 power t times. So basically, dp0 I equal to just parent, right? And to calculate for every other case, what we can do from the vertex E, if we want to step up for the 2 power t times, we can first step by the 2 power t minus 1, and from this middle vertex we will step for this the same number of times, so this will make us the step by 2 power t. So we can write it as a formula. And for simplicity, let's say if the vertex has no such a parent, so for example, if this root is our root, and from this vertex we are trying to step by 2 power 2, let's say that this link will just point to the root. And everything will still work fine. For example, if this will be the middle vertex, in this case, we will just leave here and nothing breaks, and we don't have to consider any cases. So we'll use this formula, and I guess we have some technical problems. I'll try to speak louder, and to provide that usage of this formula will always be correct, we'll just need that when we are calculating for the some specific when you calculate for some specific t, you should have provide that you have already calculated for all smaller t. So to apply this formula, you will just basically have 2 cycles. One is for t from 1 to log, and the second one is for all vertices. So this way we will calculate all the steps. And look, when we're going back to this method, when we have 2 vertices and we want to find the lowest common ancestor, first what we can do is to move these vertices to the same depth as the vertex V by not just taking smaller steps by 1. We know exactly that we know to put this vertex up exactly for d2 minus dv steps, where d is the depth of the vertices. And what we can do, we can just use a binary step for some 2 power t, where t is the largest number, which is smaller, so that 2 power t is not greater than this number, and t is maximum as possible. So which means that t is just a logarithm, binary logarithm of this value rounding down. And to do this, we don't actually have to calculate the logarithm. We can just try all the t's from the largest to lowest. Take this one, this one, and so on. We can try all of them and check that after we are moving up for this amount of steps, that we will still be not above this vertex, and if so, we just step and continue forward. So in the end, we will know, we will stop exactly at this vertex, which is the ancestor of the vertex u, and which is at the same depth as the vertex v. And after that, we will have to move up both of the vertices simultaneously until when. So, for example, consider that we have moved these vertices at the same amount of steps. We can either go here when they did not reach the common ancestor yet, and we could hit here when they already hit, not maybe hit, but they definitely passed the common ancestor, and in this case we know that they will hit exactly the same vertex. So our goal will be to hit exactly this pair of ancestors. Yeah. Our goal is to hit exactly this pair of ancestors which are not merged yet, and still they are the higher one. So after we do that, we will know exactly that the lowest common ancestor is just a parent of both these vertices. And how to do so? We have again vertex v, vertex u, and we will iterate over all our steps t from log to 0, and we check for the parents of these two vertices. So if they are did not mesh, this means that we hit this case. And in this case, we can reduce our problem to the same one. So if we just translate the pointers and be here, we will have the same problem, right? But we know that we have decreased the length from the vertices to their lowest common ancestor at least in 2 times. So if this condition holds, we can just move this vertex here, and we do the same for the second. And at the end of this cycle, we will have the case where our pointers will point to exactly these vertices. So it will take us only one ancestor from any v or u, it doesn't matter, and we will get this common ancestor. So this will just return the result, and this will be work always except the case when the one of the vertices is the ancestor of the another. In this case, after we put up the vertices which is lower to the same depth, they will coincide at this moment. So before the cycle, we'll have to do only one check, is whether the vertices are already matching. In this case, we'll just return any of them. So to provide this method working, we'll have preprocessing to calculate all the binary steps. This will take log this parameter, the log size, and second one is just any vertices. So the complexity for the preprocessing will be n log n. And for each query, we will have to go up one of the vertices. We will do this by one cycle for the size of the log. And to move up the pair of vertices is just another cycle, so it's just two logs. So synthetically, it's just a log to answer the query. And for example, this provides as a solution for the problem which I talked at the beginning. If we have to find the distance between two vertices, we'll preprocess all the binary steps, we will preprocess the depth, and we will preprocess the distances from the root to every node if the edges have weights. So, and once we have to answer the query, we find its lowest common ancestor, and from this we just return the distance from the root to one vertex to the other vertex and subtract twice the distance to the common ancestor. Yeah, so that was the most common way how you can solve this problem. There are several other ideas, and there are several improvements for this method, which we will talk right now. But first, let us consider some maybe simpler problem, or the one problem we have already talked in this case. The problem when we have a tree and the problem when for some specific vertex v, we want to find its parent, which would appear if we go up exactly k times. So if we already preprocessed our binary steps, we know how to answer the query if k is the power of 2. So if the k is equal to some power of 2, we can just return this value, right? And if not, we can still split the k by the power of 2's and combine like step this, and from this we step here, or maybe if it's not 5, it will be just a little bit more quite number of steps, but it still will be asymptotically log. And now I'll tell you how to do it in the constant time. But still, we now imagine that we have this preprocessing. Preprocessing will be n log n still. So let's split our tree in following way. Let's consider we have some tree. We will now split our tree into the paths. If someone is familiar with the highlight tree decomposition, here we'll have the similar approach, but for the different result. So for each vertex, we will pick the one from these children that has the largest height. by the height of subtree, I mean the largest depths of any vertex in this tree. So, for example, here this tree has the largest height, so we'll move here from this vertex. This tree has the largest weight, so we will move here, and so we will have this path. And actually, when you program it, it's easier to pick where should we point if we go recursively or from the bottom to the top. Because if you go from the bottom to the top, you will already know the all heights for all your children. Have a question?
Can you write a little bit bigger?
Can you see it more closely? I can try, but I can't guarantee it. And so, continue. For this vertex, they have in the same height. So, let's do this, for example. It will be the separate path, and here it's also this path and two smaller paths. And after we did this, we will write this path into the memory consecutively. So we'll just arrange some array, and we will place all these passes from our decomposition to this array. So if this is, let's enumerate the 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. Here we'll have 1, 5, 10, 11, 12. And here we'll write this as 2, 4, 3, separate, 6, 7, and two more separate passes, 8 and 9. So after we rearranged these passes to consecutive memory, we can answer this query if it is inside our path. So, for example, if we from the 12 we have to find any ancestor below that 1, 2, 3, 4. So if the key is smaller than 4, we can already answer this query in constant time, because they are just consecutively in the memory, and you have random access by this path, so you can just calculate what index will be in the hour of the hour ancestor. And if you wish, you can just use this approach further. For example, if you see that the ancestor is somewhere outside our path, so you can just move to the end of this path, then just iterate manually by using parent links, and just try to look further this way until you will have that your ancestor is inside your past decomposition. But this approach can work slowly, so there is a worst case where this approach will give you this complexity, which is for sure not what we're going to do here. And to improve this approach for each path in our decomposition, when we before writing it into the memory, we will adjust it with some more elements from the top. So if we have the path 6, 7, we will continue it with the top vertices. So we will have here 5 and here the 1, but only for the size equal to this, to our length, to the length of this path. For example, if we had here some more vertices, we will not include them to this path. So we are adjusting like that all our passes, and we'll again write them into the memory, but not just the path itself, but the several vertices that are above this path, and their number will be equal to the size of our path. So for this, we'll have like 2 more vertices. It doesn't matter which these vertices are. And for example, for the path 2, 4, okay, this will be vertex 0. And for this path, we will write 0, 1, 2, 4. And for this path with 3, we will write 2. Remember, 2 is not in its path, but we will just increase the path by the 1, because 1 is the length of this vertex. And why are we doing so? Because once we will have some query. So imagine we have some vertex V, and we have to go up to the P. And let's assume that we will look at the path in the decomposition of our vertex V. It may appear that our ancestor is not in this path. So we could not access its ancestor by the constant time. But what we are doing, we will make one binary step. So we're going to make the step by the T. Is not larger than our required step size, but it is largest as possible. So for example, we have moved here in this our V U. And let's see what changed. Now we are looking at the longest path U. It may be our ancestor may not be included in this path still, because we don't know anything about what is above this vertex. But we know that the path, the longest path starting from this vertex, is at least 2 power t, because we had this deep vertex which we stepped from. So this guarantees us so that this subtree is deep enough. So in this longest tree we will have adjustment of enough size to have this vertex. So what we if we first do exactly one step, binary step, and here we just look at the path of vertex Q. And it's guaranteed that in the adjustment of this longest path, we will have our required ancestor. So this approach provides us to find the ancestor of the required distance at the constant time, but we still have to reprocess all the binary steps, which is n log n. And here is a maybe important, maybe not so trick how we actually find this t so that it is not increased in decay and the t is maximum. So it's just basically a logarithm rounded down, but how do we find it without calling some arithmetic operations, which is slow, which is naturally why we don't want to do this. Yeah, exactly. We can also reprocess them, and the formula is very simple. So we just say that log for 1 is 0, and log for every other number is just 1 plus log I divided by 2. Here's rounded down. Yeah. So by this simple reprocessing, we can know the logarithm for every size which we could require. Okay, so now let's talk. Okay, one more interesting trick. Now let's return to our problem LCA. Now we want to improve this part. So we still want to call the query LCA for log n time, but this time we will optimize the reprocessing without logarithm and both time and memory. Yes, I forgot to say that this approach also requires this amount of memory, which is sometimes not very good. But this is the following feature that provides us to remove logarithm from both time and the memory. So let's imagine we have some tree here. Let's take some constant. Let's pick the constant, which will be about log n. Yeah. So once you know which is the sizing of n, you can pick the appropriate constant. So sympathetically, it will be log n. And our goal is to choose some vertices and make them special, so that if we will start moving from any vertices up, we will find the special vertice in less than c steps. Question? if I put it closer, then you'll stop hear my breathing, which is I not really want. Oh, here. So our goal is to pick some special vertices, and so let's call it some set as special, which is a set of the vertices. And we also want that this size of our set will be not larger than n divided by c. So how we do it? For each vertex, again, we calculate its depth. So it's 0, 1, 1, 2, here's 2, 3. And actually, you take this depth modulo c. So we'll have 0, 1, 2, 3, and c minus 1, 0, 1, 2, 3, c minus 1. And let's just count how many reminders, how many vertices for each reminder we have. And so just count them. G is a number of such I, so that the remainder of its depth modulo c equal to G. Yeah, so we count all the reminders. And we pick the reminder which has the less vertices with such a reminder. So then we pick some reminder R, which is indices with the minimum in among these counters. So, for example, here it will be 1, right? So let's consider the case when it appears that R is 1. So we pick all the vertices which has a reminder 1, this, and C could be like 4. That's all. 3. So we pick this line and this. If 3 grows larger, there will be some more layers. So we just pick some layers of the vertices and make them special. Since we have picked the vertices in this way, they have the distance from the one layer to another equal to c, and which provides us the condition to be true that if we stop iterating from any vertex, we will meet the specific vertex in less than c steps. And we have already specified this condition by picking the set with the smallest size. So this basically splits our vertices into the C groups, right? And after that we pick in the smallest of them. So we for sure know that the size of the smallest is not greater than the size of the average, right? And what we're going to do next? If we have a query of, let's say, problem, and if our vertices are not special, we will just go up until we translated them to the pair of special vertices. And we will do it. To do this, we'll just spend not more than c time for each of them. Right? So here we spend c to c. And now we are standing at the special vertices, And again, we're doing the same, but now we can compress our tree to make it smaller. So from this tree, we will make another tree with the same vertices. For example, if this vertex is this one and this one is this goes here. So in our modified tree, it might not be a tree, but it will be actually the forest. We will, from the vertex, we will store the link to the nearest special. Yeah, for any special vertex, we'll just store the nearest ancestor, which is also special. So, it cannot be the tree, and the vertices, not all of them, but only the special ones. And here we'll have like the similar. If for example here will be some more special vertices, and they will increase our smaller tree as well. So here it might not be the tree, but it might be the separate trees. But still, once we find the nearest ancestor for each special vertex, then we will do the binary step approach for all special vertices. So if we can move from our vertex by C in the original, if we already know it is a smaller tree, then we want to pre-calculate all steps by C multiplied by any power of 2. So we just basically apply the binary step approach for our smaller tree, for only special vertices. And after that, once we want to find the lowest common ancestor, we will do the same binary step approach to find the most upper pair of special vertices, which are the ancestors for our pair of special vertices, which are not merged yet, right? So if you have this also special vertices on the space, so again, using this binary search, we want to stop at this pair, not this, but at these two. This will also require our log time to make a searching. It actually will be log of the n divided by log, but it doesn't matter because it's lesser than the C, which we already spent. And after that, once we found this pair of special vertices, here is only a small part left, so its size is smaller than C, but not greater. So we can do it again manually as we've done here, to iterate just for its size. So as you see, the query is still log plus log plus log, so it's just one log. And for preprocessing, let's see, we have like n time to calculate the special vertices to find it, and we can actually find to build the tree in just n. For example, when we're doing DFS, we just keep the current stack in some random access array, so we can easily get the required ancestor. And after that, we are doing the binary step preprocessing, which is log for our parameter t. But the size of our tree is n divided by c. And c we picked in such a way that it is equal to log or near the log. So we can replace c by log and see that our preprocessing requires n time and memory. So this tricky way by picking the constant provides us a way how we can decrease the usage of time and memory for preprocessing. And maybe it is not that useful for any problem that requires us to solve the same problem. But it's just an interesting approach that can be used in different tasks. For example, I've seen a problem that requires us to answer the specific query for each pair of vertices, and the query was a little bit complicated. For each vertex we had the natural number and the query was to find the smallest natural number that is not represented on the path. So this problem was pretty hard, and it was even hard to get anything better than the just linear time by the query, but it could be a little bit reduced if we pick the constant c by the square of the size and doing the same thing, just split our path by these layers, and you can preprocess the set of the integers on the passes from one special to another special and store it like in a bit set. So after you decompose this path into some trivial part of the path and some part which is going from one special to another special, you can preprocess the bit sets for these pairs, and after that you can just merge them a little bit faster, so it will decrease the complexity from just n. It could be done to solve it to like square n multiplied by the size of the it's like this one. So the approach itself is pretty interesting by dividing this tree by the layers of the smallest reminder, and after that doing some optimization on the some common queries. Okay, I think now we are going to have a 10 minutes break, and after that we'll consider talking about different problems and ways how to solve it near this RCA problem and the queries on the trees in whole. Ready, everyone? Okay, let's look into another way of solving a CA problem, which leads us to the statistically optimal way of solving this problem. So let's consider we have a tree, and the next approach is using this method is called input and output time of the vertices in the order of deep search or DFS. So if we had a tree, let us define the order of which our DFS algorithm will process these vertices. So this one is the first. Yes?
Could you please speak a little bit louder?
Okay, I'll try. 1, 2, 3, 5, 6, 7. And let's create the list of the vertices in which our DFS will proceed them. But not only the input times, but every time, let's show how the DFS will work. So it's first with the vertex 1, then goes to vertex 2, then 3, but after the vertex 3, it returns back. So once the DFS algorithm will return back, we will also write down its parent. So the vertex the vertex above the edge after the DFS returns from this edge. 2, 4, 5, then again 4, 6. Actually, after the last vertex, we could also write here 4 one more time, but it is not necessary. For when you program, you can do both ways, but now I'll just skip them because to make this list shorter. And again, after 6, we return to 4. Yeah, I'll write 4 here, and yeah, okay, I'll just write it everywhere. 2, 1, 7, and again 1. And with this list, let's just write down the depths of the vertices. So it will be 0. This will be 1, 2, 1, 2, 3, 2, 3, 2. Like this. And if you're looking to find the lowest common ancestor of, for example, this pair of vertices, we will look to our lists at the position when this both vertices first occurs. So 3 is occurring here, and 5 is occurring here. And if you looked at the segment of our list between these two positions, and we can notice that our lowest common ancestor will be exactly the vertex with the lowest input time. So these are not just the numbers of the vertices, but it's their input times. So we have renumbered these all vertices according to the order of our DFS algorithm. So they're not just their numbers, but their input times. So the lowest common ancestor will have both the minimum input time and the minimum depth. So that's how we can define it, and how to actually find it. We will use some additional data structure. So after creating this list, we are facing the known RMQ problem, which is a range minimum query. So for the two indices in the array, we have to find the minimum value in the segment between these two elements. And I believe Andrew has discussed the ways how to do so, and one of the ways was sparse table. So it has some similarity with the binary steps approach. So it also splits segment in the equal parts, and if you know the asymptotics, it is an logarithmic preprocessing time and constant time for the query. Right, so after we found those lists and we built a sparse table data structure among them, so here you, until this time, you do not have actually consider this second array. You could just do everything with the input times, just find the list of input times, build the sparse table on this, and once you have LCA query, what you have to do, you have to find what was the input time of this vertex, and find also the position, the first position in our list of this vertex or of its input time. And after that, you just put the query to the RMQ, our sparse table data structure, to find the minimum element. And after that, from the input time, you have to restore the actual number of your vertices. But why did I mention this list of the depths? Because it can help us to solve the problem even quicker, to reduce our preprocessing time. So again, let us imagine we have this list here, and let us again pick some constant, and let us say it will be something about log n. And after that, we will split our list by the blocks of this size C. And what is interesting to notice about this array? So it is not just some RMQ problem with random data. You can notice that every element in this array is either previous plus 1 or either previous minus 1. So we can use this. Okay, so again, let's consider that we will have some large query on this segment. And what we're doing, so the end points of, any segment, any smaller block will be either fully outside, fully inside our segment, or it could be partially covered. The only way that it is partially covered, it is not prefix or suffix when it fully contains our query. So we will consider this case separately. For now, let's think that we have some suffix of some block, some prefix of some block, and some segment of blocks which are fully inside. So to find the minimum element among the blocks that are fully inside, we just just replace all the block by just the minimum element, which provides us the same list, but where each element is just the minimum of the block. And the size of this array will be n divided by c. And once we have to find the minimum element among the blocks that are fully inside our query, we'll just look at this array and it became just a minimum query on the sequence. And to solve this problem, we'll just use the original sparse table. And again, once this size of this array is divided, my logarithm the whole time sparse table here will be just n. That's a similar trick as I showed you before. But what can we do for the blocks which are not which are only partially covered or by our query? So it can be prefix or suffix, or if it's inside. Here we will use the thing that the numbers in this array are always previous plus 1 or previous minus 1. So let's consider the block, and let's say we will subtract the first element from any. So we just save the first, which is like first element of this block, and for any, let's just subtract the first. So after that, the first becomes 0, it will be always 0. And for everyone, it will be just previous plus 1 or previous minus 1. Right? And you can notice that the actual value of the first, it does not influence the index of the minimum. Now it only depends on these plus 1s or minus 1s. So the next interesting thing you can notice is that there are only 2 power c minus 1 different blocks. If we consider the blocks equal, if they have the same sequence of plus 1s and minus 1s. And only this defines what would be the minimum for any query, for any small query inside this block. Right? So what we are going to do, we will remember for each of these blocks what would be the answers for any query inside this block. So we just try any of them, and for any of them you just also iterate over any pair of the indices, which will be like C square. And for all of these cases, you will remember what will be the minimum. And after that, to actually find the minimum, you subtracting the first element, or not even subtracting, just you don't care about the shift of these elements. You only care about this sequence of plus ones and minus ones. You see in our pre-processing what answer did we get for this pair of indices, and this way you will get the answer for the block which is partially covered. And let's calculate the asymptotics. So, as I said, here we can see about the log n, but let's maybe take divided by 2. And after that, let's calculate the asymptotics. So this is our size of our block, and the number of blocks will be 2n divided by block, right? Just divided n by this number. This is the number of blocks. Okay, let's calculate what would the sparse table work for this array. It's just multiplied by log of this number. And we can say that this is just not greater than log n asymptotically, and we just can reduce these two multipliers. This provides us just to n, which is log n. And what about this part? So we have 2 power log n divided by 2, which minus 1 blocks, but you can just say it's a little bit larger than that. And this is about square root of n blocks. And for any of them, it's just log n divided by 2 squared. And this number is also asymptotically smaller than n. Of course, for some smaller n, this would be larger. So this, again, this returning us to the question whether this method is always the best one. We achieved that it is asymptotically the best one, but practically it's up to you. You have to consider if n is large enough, this method will be better. But if, for example, you have smaller n, the method we previously was talking about, which is asymptotically not optimal, could show us the better results, because the data is not large enough. So this way we have looked how we can reduce the LCA problem to RMQ problem. But actually not RMQ, but let's say plus minus 1. So it's just some case of RMQ problem. And the interesting part is that if you take the problem RMQ itself, so you have array and you wanted to find the minimum element for the query. The interesting part that the RMQ problem could also be reduced to problem LCA. I can show you the idea how to do it. For example, if we have an array and we know the global minimum, for example, it is here. We just pick this element as the root of some tree, and we'll put all the elements from the left somewhere here, all elements from the right somewhere here, and recursively apply this search to build the whole tree. So here we'll find the smallest element in this part, take this as a root of the subtree, and again we recursively construct the rest of the parts. And to actually find the minimum on the subsegment, it appears that in terms of this our new tree, the problem becomes is just to find the lowest common ancestor. So for example, if we have a pair of this and this, their lowest common ancestor will be this element, and it appears that it would be exactly the minimum element on the subsegment between these two indices. So if we can construct such a tree, this means that if we had previously this RMQ problem, after constructing this tree, now we are back to the LCA problem, and since this problem is also just corner case of this one, this proves us that these two, or maybe three problems, LCA RMQ and RMQ plus minus 1, they are equivalent, and both can be solved by the linear preprocessing and the constant time to the query. And the only part which is left is how to build this tree, and it is also a known thing. I will not cover it right now. And if you notice that if you imagine for each element that it has that the value of this array is some key, and actually the index or no, this one is the key, and this is the priority. So this tree will be exactly a Cartesian tree for this set of elements, and it is also a known thing how you can build the Cartesian tree if you have they're sorted by the keys. But here it is also already sorted because we have it there in ascending order, and just another thing we can discuss it later if you wish. but it's possible to construct such a tree from the elements if they are sorted by the key. Okay, I guess it is all about the LCA problem. We can just talk a little bit more about some problems that are close to this one. For example, just any or almost any problem about the queries of the tree. For example, you have a tree and you want to find the maximum element on the path. So this is U, this is V, and we want to find what edge or what the vertex on the path has the greatest weight. So first, what we are going to do is to find, of course, its LCA. And after that, we just split our query into two queries, where one of the vertices is the ancestor of another. And after that, for example, if we need just to find the maximum, we can improve our ideas with the binary steps. So when we are going to step for some size, for each step we will store what was the maximum element that we have skipped by this step. So the formula for this preprocessing will be pretty similar. So since I've raised, I remind you what was the formula for the step itself. And for min would be minimum from the smaller step and from the smaller step but from the middle. So when you will be climbing up to the LCA, you'll just collect what was the minimum values you have skipped, and after that you'll just take the global minimum among all of them, and this provides you with the global minimum on the path. But this trick works well if the weights on the edges of the vertices are constant and there is no query that changes them. And if it appears such query that allows you to change or requires you to change the weight, it becomes harder to use this trick. Of course, you can still use LCA by this binary step thing. But this approach only works when the weights are constant. Okay, let us consider another problem maybe. And the problem will be so, since we've already discussed the problems with without changes, that this problem contains some query that modifies the tree. So the query number 1 is to increase inclusive for sub tree. So if we have this vector z, this query should increase the weights of all elements in the subtree. And the second one is just to know the weight of some vertex b. Have you seen the problem like this before? Yeah. And do you remember what was the intended approach for this?
You can build an array like the one before you build after putting the brackets, but now just with the input in the size of the now you have updates already.
Yeah, okay, I got your idea. Now let me explain it more clearly. So again, as I was talking about the order in which we traverse the vertices in the DFS. So if we had a tree like that, we would write down the vertices in order when we first visit it, and for this problem we don't have to write it several times. So only once we visit the vertex it's the first time in our DFS order, we'll just put it in the list. So you have 1, 2, 3, 4, 3, 4, 1, 2. So for this tree, we will just give 3, 4, 2, and 1. But you also remember when you have visited all the children in the array, you want to remember what was the pointer, or I guess how many elements did you write. So for this vertex 4, you know that the last one was this. And this means that the whole subtree where 4 is a root is located as a consecutive segment starting with 4 and ending with the last added element. So once we reordered the vertices in this order, the first query is just becomes find the segment what this corresponds to the subtree and add a constant here. And the second one is just to find what was the value. And to solve this problem, you can use either a segment tree, or particularly this problem could be solved with a Fenwick tree. If you change this query, so this pair of queries can be changed. Like for this first one, we are doing plus C in the beginning of the segment, and minus C at the last element plus 1. And the second query becomes to get sum on the prefix from 1 to B, which are just typical family tree queries. So this is another way how you can use this reordering of the vertices of the tree. Because in this way, this changes the queries from on the subtrees to our typical queries on the segments with the array. So I guess it's pretty much all for today. I think today it was a shorter lecture because we did not solve some problems. For the further days, I will spend around half time between discussing the previous problems, and we will pick some topic which I probably already guess what we'll pick on the from the problem sets that I prepared, and we will split our time between discussing and focusing on a more specific topic about one problem. But I guess for today it's just that it. You can ask me any questions that you want, and I'll try to answer them. Yes. Do you want to use the mic? I've uploaded the problems to Code Forces, and I've heard the platform is convenient to you, so I hope it will be not a problem. And I'll just put them in the group, so you'll just have to enter the group once, and you'll see all the contests. You know, yes, you okay. So I don't know what you probably will have some free time, but now yes.
Is there any similar approach, maybe problem to like add or remove nodes?
Removed nodes?
Yeah, like is it hard to handle that in?
Well, everything I was talking before are related to the problems where the structure of the tree becomes unchanged, actually. And it becomes a lot more complicated if you can erase or even add nodes. But for example, this approach with binary steps works well if we, for example, can add more vertices. So if you have some tree and you want to be able on the add vertex, so everything you need to do with this new added vertex is just to pre-calculate all the steps from it, and you can always do so because you have already calculated all the steps for previous ones. So if you just recalculate the binary steps for this newly added vertex, you can still calculate the LCA. But once you want to remove something, it becomes very gross.
Do you have any interesting problem that you know about high-byte composition?
Maybe Do you wish them to see in one of the contests?
Nice.
Yeah, it's fine. I can look for it. Yes, and I will. The contest you'll solve, I guess, it's mostly picked from the some past context, but sure, if you have the suggestions for the topics, I can look for the contest where it has such problem, or even which we can just merge several problems for everything for you. Yes.
Could you provide maybe quick proof about why in the LCA problem, when we stored an array with the longest path?
Yes.
Why only one binary step is necessary?
Yeah, because by the definitions, look, if you have a vertex and it points somewhere, it points to the subtree with the largest height. And if we have stepped here by some power 2, which is, as you remember, if we want to step by k, but we only step by 2 power t, and we could not make the larger step, this means that 2 power t plus 1 is already larger than k, right? And since we have stepped to this middle vertex from here by the 2 power t, this make us sure that the length of the path from this vertex would be at least this size, because here we have at least this height, but the longest will be not the shorter than this one. So that this makes us sure that the length of this path, like which goes down, is at least 2 power t.
Because you can only go to longer paths afterwards. If you jump from one path to another, the one on top is longer.
That one was unclear for me. But
if you are on the same path, then you can just jump in the array, and it's okay. But
yes,
the problem is if it is on another path.
Yes, but that's why we have to for some paths. That's why we used this approach. We're not just staring the path itself, but we also increasing it up for the same size. So when we write this path, we will write some additional vertices before it. So some vertices could be write down several times, it's okay. But since if this vertex is the middle vertex after we have stepped, we know for sure that the rest number of times we need to step will be at least in our additional vertices. It might not be in this path, but it will be in our increased path. And with all these additional vertices we will also write just before this one consecutively. So this provides us the random access to this ancestor. Just some trick how to not step more than once and to step between the paths. We just adjust our argument all the passes by the equal size.
Write an example of this construction of some tree that you
think I did it in the beginning.
This partial is not very good.
So I had this example. So it's better for us when we are programming to do it from the lowest points, because we're probably going to calculate the space using the dfs. So first to calculate to which parse belongs this vertex, we are probably going to calculate everything that is below us. So this creates us its own path. For this vertex, we have only one children, so we merge the path into this one. Here we have, okay, this will create our separate path. So the number of paths will be equal to the number of leaves, exactly as in the Hewlett comparison. Here we will merge with the longest. This is length 2. Here for this, we'll create our separate. This will merge with any one. For example, here, this one again, this could be separate. This merges here, and for this one, we just pick the largest one. So we just look at the number in the root, which will store the length of the current path. We will pick the largest, as this one. And for example, even if we have here some one like this thing, if we want to calculate, for example, from this vertex, we want to jump for 4. Not by 4, but that's 5. No, not 5. Okay, it's 3, but it's a very poor example, but I think it's not. So we will step here. And from here we need to step by one more, but in this path, which contains how many? 4 vertices. We will have 4 more from these parents. So to get the access to the ancestor, we can just take the random access from the memory, because we will have for sure. Yes, and as you see, I kindly illustrated the worst case. If we will just traverse between the paths by manually using its parent, it can be the case when we will visit square root of n paths. If this will be like length 1, length 2, length 3, length 4, it can construct the worst case in this approach.
So what's the complexity about the memory of this construction?
Well, if you want to use this, you probably are going to construct the binary steps preprocessing, which is the same memory and the time. And for query, you just need to one step for the largest, not exceeding the required amount, and plus 1 to get the access to find the actually find where is the path the current middle vertex belongs to, and after that to get access to the answer. So just like very small number.
That's for the query.
Yes.
But you have to start the list of the vertices. When you have a chain, you have to have in memory on an array I suppose if the chain that you have I don't know 4 elements, you have to store the 4 ancestor above the head of the chain.
Oh, what is your question is about query or about the web processing?
Web processing.
Yeah, so this is only for binary steps. For constructing the longest path itself, it's only n, because for each vertex you just one operation to understand to which path it belongs to, and once the path is about to finish, you will just find some additional vertex which equal to the size, which would be just the length of the total length of this adjusted passes will be just 2n, because it was just n for separate decomposition, and it's just the same amount you have to add, so it will be linear for just constructing. So, if you don't have any more questions, we'll see you in the contest. Today probably will be no program for this topic, but for the further day, I'll definitely pick something.
Everyone, since we have a bit of time, we'd like to take a group picture of Class W. So if you could all go to the steps in front of ICPC. We'll take that down. Thank you.